my account.
That's good. That's good. I got it. This time I remember.
No, Victor is the pro now.
I know.
No.
There's still no update on my internet, by the way, so you might be doing this for a little while longer. Sorry.
Okay.
They're going to come on the 20th again, but they already told me they're not going to fix it. They just have a look. So,
all right.
Yeah, we'll see. Right. This is filling up nicely now. So I think we can make a start. Welcome to Neuroccino on this Monday morning, the 16th of May. Today, Victor volunteered to present. He is a PhD student at the University of Bordeaux. And today he's going to take us way out of our comfort zone. At least knowing the background in this audience, half the group will be out of their comfort zone. But even though we're going far away from the brain today, I just want to remind people, especially those of you who use diffusion imaging, that looking across our own discipline and horizons is actually important, because some of the algorithms that we use, like the Richardson-Lucy algorithm, actually was borrowed from astronomy. So Victor, if you're ready for takeoff, take us into space today.
Thank you. So today's Neuroccino won't be about neuroscience, as Steffi kind of pitched it. It will be more about astronomy, because one of the biggest piece of science news that we had last week was about the first image of Sagittarius A star, meaning the black hole at the center of the Milky Way, our own galaxy. So for me, it was extremely exciting, because this is something that I really like to look about. And I mean, the astronomy, astrophysics, for me, it's fun stuff. Like, it's the stars, it's big, it's how the universe works, and it's really cool in general. And well, this one is our own black hole in the center of the Milky Way. So, well, first, I'd like to show you what the image looks like, and then we'll talk a bit about what it is and what's the black hole and everything. But first, the picture. So where will I? There is so many things open here. Well, let's say go for the desktop. And here we have the image. Can you see it, right? This big blob of black with a bit of yellow orange in the middle, donut shape, and the black in the middle. Yeah, so that's the picture that we have from the black hole in the center of the Milky Way. So first, what's a black hole? A black hole is basically an object that is infinitely dense and that warps space-time around it with its mass, so much that basically light can't escape it. So depending on its mass, the radius of the area where light cannot get out of it is more or less bigger. Like, the bigger the black hole, the more massive the black hole, the bigger this area where the light cannot get out. And the boundary of this area is called the event horizon. And as a matter of fact, the telescopes that were used to image this image were called the event horizon telescopes. So this is why. And you might wonder, but if light can escape from a black hole, how can you image anything? Well, you'd be right. We can't image actually the black hole itself. What we can image is the matter that is surrounding it, because there is always a little bit of matter surrounding, well, not always, but often a bit of matter surrounding black holes. Sometimes they have a large amount of matter, sometimes a bit less. In our galaxy, it's not there's not that much matter, but there's still some. And the thing is, because it's extremely massive, any matter that is coming close to it is extremely accelerated, and the matter that stays around it is orbiting it. But because the orbit, of the mass is so important around black hole, in a black hole, it means that the orbit, if you want to keep some matter around it, it has to go really, really fast, right? And actually, it's a significant portion of the speed of light, the speed at which the matter is orbiting around the black hole. So it's crazy fast. And well, this matter going extremely fast also collide with each other, and all particles collide with each other. It creates heat, and actually it creates extremely high heats, like millions of degrees, higher than in the sun, for example. And this heat radiates light. And so what we see is what we call the accretion disk that is surrounding the black hole. So basically, you could say that the black hole itself is like the dark zone in the middle here, and the more colorful donut shape area is the accretion disk. So now you might think, okay, I got the picture. So basically, the black hole is facing us, right? Because we see the accretion disk, which is a disk, so it's on a plane, and we see a donut shape. So you might think it's the case. Well, actually, well, kind of, but the story is a little bit more complicated than that, because of the way the black hole warp space-time, and the light that is emitted by the accretion disk can actually kind of orbit itself around the black hole, and you would actually kind of see the donut shape about everywhere, where independently from where you would be looking at the black hole. It's a weird optical effect of black holes. And thing is, well, the first paper that was just published with this indicated that they estimated the black hole to actually be kind of pointed toward us like this. Like they say it should be about 30 degrees from being straight on toward us. So that's actually pretty neat. And the thing is, it also means that it's not aligned at all with the rest of the plane of the Milky Way galaxy. And this is something that also was somewhat known for black holes, like their orientation is kind of independent from the galaxy they are in. And so this image is quite incredible when you think about how far it is from us. It's I don't remember exactly the numbers, but it's several dozen or hundreds of thousand light years away. So thousand or 100,000 light years away, meaning that the light that's coming from this took, well, as I said, 100 or dozens of thousands of years to come to us. Just think about it. It's so far that light just took a huge amount of time, and yet we managed to image this, to take a picture of it. So also, disclaimer: this is not a real light picture. This is actually false colors, because this was taken through radio telescopes, not normal normal light telescope that you could have, or even infrared or anything nice. We are talking about radio telescopes. And I want to show you something about how the image is made. Actually, it's not like one telescope that is doing it. It's about telescopes all around the world trying to capture this data around at the same time. And what they do is try to use something called interferometry to combine the radio signal from the different telescopes to get an image. So here is a short part of a video that I put inside of the in the chat that explained it quite well, and it's just a short part. And I recommend you highly to watch this video. It explains a lot of things about what I just told you about, and just this snippet is, I think, quite nice to visualize how the physics of this image was got. So I don't know if you'll have the sound of the video, but if you don't, just try to sign me to show me with your arm, and I will tell you. Okay, no sound. So I'll do the, I'll tell you exactly what's happening there. So here, they're taking the example of two telescopes and that are trying to get a signal from a distant object. And the signal must be, they try to have the signal in phase. So they say, okay, when the signal between the two telescopes are in phase, it means that the object is at a given distance that they know and they can image it. But one problem is that you've got not exactly one point in space, but actually a disk all around that goes through the middle of the two telescopes. But it's worse because actually it could be higher or lower depending on the interference, because if you got the wave that is synchronized, it can be just because it travels the same lengths in both directions, or because there is one more or one less or wavelengths on different on the reception. Well, it's a bit technical, but basically it means that you can have several fringes of interference appearing between a pair of telescopes, and so it's not super good. The results you have with this is not super informative. You'll end up with this kind of fringes like this. This is far from the image of a black hole that we just saw, right? And but the thing is, they have several telescopes, and they have they have several telescopes, and depending on their distance between the telescopes on Earth, it will be different orientation of the fringes and different size of the fringes. So when you have a lot of telescopes around the whole world, you can have a pretty good thing. And when you combine the different fringes, what happens is an image of the black hole, which is pretty cool when you see it like that. I mean, for physics nerds like me. And so this is actually another image of a black hole. Yeah, it's not the same black hole. I think it's the M87 black hole that was imaged in 2019, which is way outside of the galaxy, but it's another story. So this is, I probably, I won't take too long again about this, but if we go back to the actual picture, you also can see like whitish spots, like blobs that are with a brighter color, and these bright spots are basically matter that is clumped together around the black hole. For one part, basically, mostly like these two are probably most likely blobs of higher density matter in the accretion disk, but there is also a very much higher brightness spot here, and this is probably due to what we call excuse me, I don't remember the term, but it's basically because the black hole is the accretion disk is rotating around the black hole. When it's coming toward us, it's actually beaming photons in higher like more photons, or at least higher speed not higher speed, but higher frequency photons toward us than when it's going back. So you can see like here it's brighter, here it's darker. It's basically because this part is coming toward us and it's beaming more photons with higher energy, or even maybe more photons toward us, which means that it looks actually brighter. And so there is so much more I want to speak about it, but I could go on and on for an hour. So I'll just stay with that, and we can discuss if you're interested.
Lovely. Thank you so much, Victor. This is great. I have a couple of questions, but also so that there is a question in the chat. which is a query about the Doppler effect. Chris, do you want to expand on that?
That was the I think that's the name of the effect.
Yeah, it's Doppler beaming actually. Yes, it's Doppler beaming. Yeah, there is Doppler effect.
When it goes
Doppler
in
beaming,
one direction, the light is stretched, and when it goes in, the wavelengths are stretched, and when it goes in the other direction, they are crushed. So we see more red when it goes away from us, and we see it more blue when it comes towards us, right?
Yeah, well, more blue and more red. Exactly. The term in astronomy is what like red shift and blue shift. That's true. In this case, for actually, I don't exactly know if there is a difference between Doppler beaming and Doppler shift, because maybe there is actually more photons coming also when it's coming toward the disk is coming toward us. I don't know. I'm not a physicist, and I haven't looked into this. But yeah, there is definitely the Doppler effect, like higher frequency radio wave in this case. In this spot than in this spot too.
And if I can add, so I followed also that because I really love it as well. It's it's so passionate. It's just crazy. In I think it's in the video of Veritasium, but there is a star that they saw being eaten by, I don't know if it's this black hole or if it's the other one that you talked about, but the star was came towards like very fast towards the black hole at like 10% of the speed of light.
Yeah, 8, I think,
like
but
it's star.
Yeah, it's crazy. I think just... I don't know if it like, oh yeah, there is this thing. Oh, I just want to show you this part. My screen is still shared. Okay, so this is basically the Milky Way that we see in our sky. And here it's zooming in toward the black hole. And you can see how much you must zoom in and keep zooming in to start to see, just for now, stars. But still zooming. And so now we are reaching kind of the limits of our telescopes. One thing is cool is they did several recordings of these spots near the center of the galaxy, and they can see the star zipping around because of the black hole. And so you can see them like moving around, and this one, woo! And so this star that we just showed like this, going 24 million meters per second, 8% the speed of light, like when at the closest approach to the black hole, 8% the speed of light. It's crazy fast. And we are talking about a star, right? Something that is absolutely huge.
So 24 million meters per second. How long would it take? It would take like a couple of hours to go from the sun to Earth.
Yeah, probably. I mean, I think it's like 8 minutes to go from like the light may take 8 minutes from the sun to Earth.
Yeah.
So 8 times 0. Times 0.08.
So you times 10.
Yeah, about 10 times 10. So yeah, basically.
It would be about 2 hours or something like that.
It's crazy.
A star to go from the sun to us. I don't know if it's very. It's difficult to realize the size in space.
Yeah. It's yeah. I see that we are completely agreed on that. I'll just stop the sharing so that we have a better view of people. All right.
I don't see a raised hand, so I'm just going to jump in right now. I'm happy to see the conversation flowing. I knew that there's people in the audience who are straight in their comfort zone, so this was fantastic. You mentioned the picture of the black hole that we also discussed, I think, before Neuroccino was online. of the 2019 black hole. And you mentioned that that one is actually further away than the one you just showed us from the Milky Way. And I was wondering why we saw a black hole that is further away first.
All right, good question. It's because M87 is actually, so there is a kind of cool thing about it. It's like M87 is about 1,000 times more massive than the black hole in the center of the Milky Way, which is already like supermassive, which make it 1,000 times bigger. And it happens that it's about 1,000 times further from us than is the black hole in the Milky Way. So when you look at them, they are kind of roughly the same size when you look at them from Earth. But the thing is, we are looking through the Milky Way to look at Sagittarius A star. So you've got a lot of gas and dust and stuff obscuring our observations, meaning that it's kind of blurry and not as easy to observe as the one that we are looking actually quite straight on, that is 1,000 times further away from us. Another thing that happens is that because the other is so big, the accretion disk around it is also moving close to the speed of light, right? But it's moving relatively slowly compared to it, because when it would take a few minutes or hours, a few hours to just for the matter around the Sagittarius A star to go around it, it would take weeks for a matter around M87 to go around. So when you take pictures of M87, you can just like do long exposition, repeated observation, and just put them all together, and pop, you've got a nice clear-cut image. For Sagittarius A star, it's not as easy because the blobs that you saw, well, they move around and they change shape and everything, and in a matter of minutes and hours. So it's hard to get a good picture out of it. And so what they did is actually they did several pictures of it, and they clustered together the different pictures that looked roughly the same using some AI algorithm. And then they did several cliche, basically, like several means. They did the mean of several clusters of pictures to get more consistent, less blurry image. And so this is just one of the image that the clear image that they got. This is the one I showed you, but there are actually multiple of them. And so this is why it's actually the second thing that makes it even harder for us to image something that is technically way closer to us. But yeah.
Yes, us complaining about motion artifacts and MRI pales in comparison to them trying to capture moving stars. The other question I had for you, because I couldn't quite tell, like, you're super excited about this finding and this study, and I totally get that. But from the way you pitched it, I was wondering if you're more excited of the fact that we have the picture and we can see it, or the way they got to get the picture.
I mean, for me, it's
is it the result or the method? Or
it's both? A whole. It's both. It's. I mean, I was excited by the image because I mean we knew there was, or we already knew there was black hole, a supermassive black hole at the center of our galaxy, and the fact that we have a picture now of it, I think it's super exciting. This is what excited me a lot, but also just from the methods that they use to image this kind of thing, I also find it really interesting and exciting. And it's a whole, it's what you get and how you get, and why does it look the way it does, and all the information that you can get from it. I find it all super exciting. And the more I know, the happier I am.
Nice to hear. Leah has a question for you.
Yeah, it was more a comment about why this is so the enthusiasm is so high. It's linked to actually your question, because in physics there is a lot of mathematical, also the technical stuff, as Victor showed, and so there are really, like, it's insane how much efforts are behind just an image. So this is why then when you have the image you say, okay, so all the efforts. And also what I like is that usually you predict, these things, Victor. So there is a theory. So when you have like the general relativity, so when you have something that prove that all your equations, your theory makes sense, that is what makes you happy, I think. No, what do you think, Victor?
Yeah, it's true also, because actually black holes were stayed as theoretical object for quite long.
Yeah.
They tried to understand what was happening with what would happen with the theory of relativity and the everything Einstein's just put on the table, and say, okay, what happened if we just like put matter so close together that it goes against every other forces and it's so dense that it just collapses? And they say, oh, it creates something that warps space in a way that actually nothing can get out of a certain area around this place of infinite density. And so it's really strange. And is it possible? Does it exist? We don't know. Maybe not. And then a few years later, they detected an X-ray source coming from the Sagittarius constellation. And so this strange X-ray source, they call it Sagittarius because it was in this constellation, A star, and star meaning unknown X-ray emitter or something like that. So there's something weird there, and it's at the center of, it seems to be at the center of a galaxy. Weird. And there was theories about it being a black hole, and the more and more observation we had, the better we came to understand that the black hole were a thing, and it was probably one. And when we imaged the stars zipping around it, that was a definite clue about the fact that there was something that, one, was not emitting light because we could not see it well, and two, was extremely massive there. And so yeah, that came around from theory to practice with imaging, and that's quite neat way to explore the cosmos, I think. So
yeah, that is insane that you think about it, you created this object or this theory, and then you measure it. I'm curious about then the dark matter, how we will explain that in the future.
That's an whole other story.
That's to show the importance of a good theory at the base of your science, though.
It does. So I think Chris has the hand raised.
Yeah, what you said about the discovery of the black hole, well, because at the beginning it was just theorized that if you run the equations to the limit of energy and mass, you get a black hole. But what's also so interesting, I think, is that it breaks at this point, because we don't know. So we were able to I mean, we know some people much smarter than I am, but they were able to predict black holes, but they also predict that it breaks physics beyond what we can see. So it also created a whole bunch of other questions, and that's what I love in science. It's so fascinating, in my opinion.
Yeah, that's something that is crazy. It's like, we know that black holes exist, and we know that they form, and that actually supermassive black holes, we are not exactly sure how they form, because they cannot have been formed through a star exploding or something like that. They are too big. They are just too big. And so there's still some debate about how they form. But never mind that. What I wanted to say is that when you get to a point where you break, as you said, the physics, you actually break the theory. It's when you put infinites somewhere inside of a theory, you are in a bad spot usually, because anything can happen. And we have here in the theory, like a point of infinite density, which is kind of strange. And actually the thing is, it does not play well at all with another theory of physics that is extremely successful in its own way, which is quantum theory. It does not work at all with quantum theory. And so we have here two extremely good theory that explain things very, very well. But the thing is, when you use the theory of relativity and you go back to you go to a very small thing, it breaks down. And when you use quantum mechanics and you try to apply it to a very big thing, it breaks down. But both of them, in their own way, they are very good at showing what they were discovered for. But now they do not agree on a lot of things, and so we need a theory of everything, and we're still not there.
That there are some answers left to address.
Oh, yes.
So now that we have the picture, where do we go from here?
Ooh. Good question. Actually, I don't know what's their plan. They probably will keep imaging it to get more and more data to have a better understanding of everything about it, like how it polarizes light, what the magnetic field around it, and stuff like that. But actually, I don't exactly know where their research is going.
And in terms of science in more general, like, obviously it's a stunning picture, it's exciting to see it, but does it change anything right away, or is it more a matter of, this is super cool, we can now do this, let's figure out what we can use it for?
There is one thing that it changes. It changes, well, it's an observation, and you have to make sense of other observation that you put around. And one observation that was done quite a while ago is that around, like on top, so you've got like the plane of the galaxy, and on top and on top and beneath it, we have what we call the Fermi bubbles. It's bubbles of very hot and diluted plasma that I think it's plasma, but well, ionized gas basically, that is maybe moving away, but very hot with at least and are so below and above the Milky Way galaxy. And the thing is, we thought it was because before there were jets of matter coming from around the black hole and shooting this way, but that would mean that the black hole is in this, like, oriented, like spinning in the same axis as the Milky Way. But we just saw that it's like super tilted and more like toward us, and we are on the plane. So it's probably not that. So there was two possibilities. One is a bit unlikely, which is that between the moment where these bubbles formed and now something made the black hole tilt, but you would need a very big something, like another supermassive black hole. And so, well, it's kind of unlikely, but not impossible. The other possibility is that we actually don't know what these bubbles, like the Fermi bubbles, are, or how they were created. And so we need to rethink the theory about them. And this is very exciting about this. And I see that we have Michel who wants to add something. Go for it.
No, it's just a question. It's like,
Sure.
and it's really cool to see things really far away, but can they use the same technology to see in higher resolution things that are closer to us? Like, I don't know, Alpha Centauri, for example. I'll be happy to have a high res of the system.
I don't think you'll get a really high res of Alpha Centauri through radio wave. Because radio wave here is really to look at so multiple things. Radio wave are good in this in here, because we actually can only use radio wave, because they are the only thing that come through all the gas and dust from the center of the galaxy, and they can emit, they can image like something that is really faint and stuff like that. So the accretion is, so that's good for radio wave. But when you can look at something closer, you don't have all these dust and gas, and so you can actually use light, and this is just much better to use light in this case. So one thing that would be cool is that you can look at, we can use other kind of big telescopes to look at that, and one that was just launched a few months ago will actually look at this kind of thing. Like the James Webb Space Telescope will be for this kind of thing, will be to have like very good images of these very small, even if they're somewhat close objects. So yeah, I'm very excited, but not about using the Event Horizon telescopes, but more about using the James Webb Space Telescopes to image a closest star. So, and I see Tobias have a question or a remark.
Yeah, I want to briefly add to why we take this picture. It's obviously not just about having a picture like this, but also what was mentioned before with dark energy and dark matter. We still have a lot of effects that don't fit in our explanations about gravity. And because this object is so extreme, we basically scientists are also trying to break the theories of Einstein, because like Victor said, we don't know how it fits together with quantum physics and stuff like that. So basically everybody is trying really hard to find something that is extreme enough so that there are effects that we don't understand, which could be everything, also just wavelengths that didn't fit or something like that. So besides that, this is neat in proving our theories, we are also hoping to find something that does not fit. And also, like Victor also mentioned, there are black holes that are already bigger than they should be, like the supermassive black holes in the middle of galaxies. So having now one really big black hole and one normal sized big black hole is also neat, just for comparing if for all different sizes of them the theory fits, or if at some point there are outliers.
Thank you. That was actually a nice wrap up, I guess, and that's all we have time for today. Thank you so much, Victor, for discussing that paper with us. Thanks to the group for being so engaging. And I guess it also nicely shows how important it is to be multidisciplinary and have people from different backgrounds come together and share ideas. So thanks a lot for everyone here on Zoom and for those over on YouTube. And I wish you all an exciting week in science. And I see you next Monday. The slot is still free. If anyone comes across exciting science, do let me know. And the slot is all yours. Until then, have a great week. Bye.
Bye-bye.
Bye. That was cool, man.